is Julia Bush, and this is my Physics Lab 5. So as an introduction to this lab, some concepts we explored were Faraday's law, EMF, and magnetic flux. And we explored these concepts by dropping a small bar magnet through a metal tube covered in aluminum, and we measured the time it took to fall through the tube. So some measurements I made before doing the lab is the aluminum is 1 centimeter thick around the cardboard tube, and the diameter of this tube was 3.1 centimeters. The total length of the tube was 30.4 centimeters. And I did 5 trials dropping it through the tube, and I found the average time to be 1.47 seconds. And I calculated the dipole moment in a previous lab, but actually did it incorrectly, so I redid it to create a more accurate moment, and I got 1.6 ammeters squared. So some formulas I included here that I used in the coding were that the magnetic field of the dipole on axis is u naught over 4 pi times 2 times the magnetic dipole moment over r cubed. And I used to calculate the magnetic field to find the force for the coding, which we created a three-dimensional model of the magnet flowing through the tube. And then for this formula, it's EMF is equal to negative, and our n is 1 in this situation, times the magnetic flux over time. So using this and knowing that the current is equal to EMF over R, we can then find that this expression times R is going to be equal to our current. So I used that information in my code. I also used the expression that the magnetic field is equal to U naught times N times I over 2R. So our goal in creating in our code this week is creating a moving 3D model that displays the magnetic falling through the tube, and then it calculates the total time it should take. And it also will make this velocity versus time graph. This is what mine looked like. And if it were just gravity acting on the magnet, we know that it would be a straight line in constant acceleration. But since we see that this is obviously not a straight linear line with constant acceleration down, that's the force of the magnet and the induced current we're acting. So yeah, this is indicating the magnetic force that I calculated in the code. And the total time it calculated was 1.513 seconds, which is pretty close to what I observed, which was 1.47 seconds. So it was pretty accurate. So in conclusion, if the resistivity of the conductor had been closer to 0, this would have increased the total current because the current is equal to EMF over R, so if we were closer to 0, this would have increased it, which would have increased the total magnetic force. This is a typo. It should say this would increase the total magnetic force, since the magnetic force is I times dl times the magnetic field times sine theta. And then this would increase the total time it takes the magnet to fall, because if you increase the magnetic force, it's going to further counteract the force of gravity and cause it to be slower falling down the tube. And if you add 4 slots to the tube, this would increase the theoretical number of rings, which is denoted by the n in the previous equations. So this should increase the current. And we know this because you can see here that current is equal to R times this expression. So if you increase the number of coils in your loop, you should then see an increase in your current. So that's all I have for this lab. Thanks for listening.